Good morning, Astronomy 1020, and welcome to the week of Lecture 6. This week we're going to do some hybrid stuff. We're going to finish up the little bits and pieces of Chapter 5 and 6, which is on light and radiation. Today's lab will be a classic on telescope building. We'll get to play with some lenses and learn how to build a Keplerian refractor, just a basic kind of telescope, similar to this puppy here, except without the fancy tube. On Thursday, we will begin our first astronomical object. We will start studying the sun, the first of many stars we will study. And then, of course, it should be reminded to the class that next Tuesday is the exam. Dum, dum, dum. You've got an exam coming, and that's always a source of stress and terror for students, and rightfully so. I'll talk about the format and such on Thursday. And on Thursday, instead of doing a typical office hours where we work on a problem set, a homework, we will take a break from homework. And Thursday's office hours will be dedicated to running practice problems for the test. So we'll sort of simulate test questions. You guys will try to solve them while I stare there and look at you and say, are you done yet? Are you done yet? And then we'll see if you can solve them. And then when, of course, you can't, because you won't be able to, then I will show you how to solve them, and you will become stronger and better for the test, okay? Does that sound like a good plan? I think that's going to be a very important office hours, one that is not to be missed. Also about the test, last semester I did things a little differently. Last semester, I kind of just treated the exam kind of the way it was when I was teaching in person. That is, on a Tuesday when we had class, I gave you guys sort of the day to solve the test. And depending on whether you were a daytime person or a nighttime watcher, you could kind of do it at your time. And I even logged in and kind of muted my video and kind of hovered around in case you had questions. But that turned out to not work so well for two reasons. One, people have complex schedules and they need to take the test at different times. Some people are really slow and need a little extra time. And people are going to have questions whether they're taking it day or night. So this time, what I'm going to do is I'm going to leave the test window open for a few days. I'm actually going to open it up on Sunday because I know that some of you out there use the weekends to catch up on work. Like Nick, for instance, you were scraping to get your homework in this past weekend on a Sunday, right? So that told me that Sunday was a time where you could do some work. So I figured I could open it up Sunday, Monday, and Tuesday. You can kind of take it whenever you want. It's a long test, so it'll take you a few hours. And then I'll just be on call like a doctor. You guys on the syllabus have my phone number, you can text me, call me, or you could email me, but of course, texting might get my attention a little quicker if you have a burning question. Or calling me, just call me and say, hey, I'm working on number 5. And I'll stop what I'm doing. Presumably I'll be around the apartment because there's nowhere to go these days. And I'll be able to troubleshoot that with you. If not, you can read me the question and I'll help you troubleshoot it. Does that sound like a pretty good idea? That'll give you a couple of days to choose from, but the test must be completed by Tuesday at midnight because I have grades due Wednesday, midterm grades. Do we understand this? Okay, so you must have it done by Tuesday. So if you're a person who has a lot going on Tuesdays, do it Sunday or do it Monday or something, okay? All right, thanks, Kiana. Let's return to some subjects we left off last time and see if we can do them better, especially because I know there's going to be a few questions on the test on the inverse square law. So let me begin by showing you how do I want to do this? Let's start by showing you some slides. I thought excuse me, guys, I thought I had opened up my slideshow. Wait, I know I did. Oh, I see. It's hidden back here. That's it. Okay. So last time, in a sort of haphazard way, I talked to you guys about luminosity and brightness. And we talked about Dyson spheres. You may remember that was a fun part of the lecture. Collecting all the energy of a star is a hypothetical dream of science fiction. And we talked about the inverse square law. I happen to know that there's going to be a few questions, more than a few questions on the inverse square law on the test. And I was feeling a little bad that we didn't try out some practice problems. So if you want to get your calculators handy, that could be a good idea. Let's start with the question just to kind of figure out what you guys know. If I were to ask the question, what's the difference between luminosity and brightness? Would you be able to answer that question? Or would you be able to answer what either of those two things are? I'm not sure that I understood it perfectly the first time I learned it, so I want to see where you're at. Luminosity is the easier concept. You could start there.
Luminosity is the power of light.
Okay, I like it when you say that. I'm sorry. I just started translating what you were saying into my thing here. We're going to do a little notes here on luminosity versus brightness. As you mentioned, luminosity is the power of light, but power is a code word. Luminosity is the power of light is something that's funny or it makes sense after you understand what luminosity is. In fact, let's just take that out for the minute. It's true, but that's not helpful right now. I was thinking, how would you describe luminosity in touchy-feely terms?
You gave us a second definition for it.
Let's hear that one. I want to see what my good words were.
It says fixed property of a glowing thing.
Okay, so that's important. So here's something important about luminosity. It's fixed, and it does not depend on distance. A light bulb has a fixed luminosity. A star has a fixed luminosity. What's a fun glowy thing? The Biltmore sign over Providence has a fixed luminosity, or each letter does, I suppose. Could you describe it any other way? We got Pippa in the house. All right, here's how I would put it. It's the flow of light in all directions. So if I was trying to draw luminosity, and let's try to draw it with a light bulb. I would draw the luminosity as a bunch of rays of light leaving the bulb in all 360-degree directions. In reality, it's 4 pi stradians, but you don't know about that. That's over your head. I won't tell you about solid angle geometry today. That's L. If I say a light bulb has a luminosity of 100 watts, that's telling me that there are 100 joules of energy flowing from the bulb in all directions. It's energy flow. That's what it is. It's a rate of energy flow in the form of light. Okay, so tell me something about brightness then. Let's have some more regurgitation. Come on.
I have luminosity over area.
Okay. Brightness, unlike luminosity, is not fixed. Brightness depends on distance. It has units of watts per square meter. You might think of it as a cone of light or a square of light or a beam of light that hits some detector. In MKS units, a meter squared is roughly the size of my dry erase board. You can see meter by meter right here, right? So this dry erase board is a panel. It's bigger than a microwave, but smaller than a refrigerator, somewhere in between those two things. And this, if this was a solar panel, this solar panel would be approximately 1 meter squared. And brightness asks, how many watts are going to splash across that solar panel if you hold it up kind of perpendicular to the light source? Okay, if you spin it or rotate it, let's do a demonstration here. So this is not a square meter, but it fits in my screen, so let's pretend it is. If your camera is the light source, boop, 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 there you are, right? And the light is flowing towards me. This panel would capture some watts per meter squared. Even if it's not a square meter, it can capture watts per meter squared, right? Because if you're getting 100 watts per square meter, if you have a panel that's a 1/10 of a square meter, then you will be capturing you'll still be capturing 100 watts per square meter, but I might actually only be capturing 10 watts here. Does that make sense? That sounds a little weird, but I think that makes sense. Okay. If you twist your thing like this, you will reduce the amount of light you capture. So don't go there yet. That's for an advanced class, okay? For now, we just assume the panel is pointing right at the sun. In that case, it can be helpful to know some things about spheres. So if we want to draw a picture, once again, a picture can help us understand brightness. You imagine a beam of light coming from your light source. So here's your light source. But you just focus on one little beam. I could make the panel circular or square, but I'm going to make it square because that's easier to draw. So you're focusing on some cone of light, and you're asking how many watts of light, how much energy flow passes through a square meter some distance away. Brightness obeys an inverse square law. And that means a beam of light attenuates. Attenuates is kind of a fancy word, right? The beam of light spreads out and gets bigger and bigger. Here's a nice case in point. Let's take my laser beam here, right? This is a very powerful laser. I'm probably blinding myself every time I do this kind of thing. Let's get a meter stick, okay? And I'm here right in front of the board, and I shine my laser on the meter stick. Ooh, that does hurt the eyes. And I notice that this beam to you guys, it looks a little bit more spread out than it does in real life. In real life, this looks like a pinprick, but the backscattering is doing a funny thing to the camera. But this little pinprick is about 2 to 3 millimeters across. Even though this laser is highly collimated, meaning they've gone through great lengths to force all the light out of a very tiny hole, you can't stop the inverse square law. You can't stop the spreading of a beam as it travels through space. So when I fire it across my apartment, I like to do this demo in class, but I don't know how well it's going to work, and I wish I'd cleaned a little more, but okay. So by the time I shine it over there towards the bookshelf, that spot has grown considerably. I wonder if I could measure it just for fun and giggles and demo purposes. Maybe I could rest this thing down. Ooh, this is very clever of me. Okay, so let's go and see. Let's travel to the, oh, wow, that's cool. You can see, can you guys see the beam there traveling? That's pretty dope. Let's travel to the other side of the room and let's see how much the beam has spread out.
That looks pretty gnarly
Yeah, it's cool, right?
from here.
What's wild is the beam spread out. I was thinking it would be even more, but my apartment isn't that big. It's spread out to 1 centimeter. So if you can see my meter stick here, it went from just the spot only covered 2 or 3 millimeters. And by the time I got to the other side of the room, it was 1 centimeter. One of the things I used to love to do, if you guys are familiar with the CCRI campus, I used to love to do this demo in the laboratory because it has glass windows that look out into the Great Hall. And I would send some poor student running across the building to the other side and stand on the ramp. And if you go across the width of CCRI, the beam will spread out to be like maybe 10 or more centimeters. So it's really, really dramatic, you know? Sorry, I got a hair in my mouth and it's bugging the hell out of me. One of the reasons why you can get in trouble with these things, especially if they're more than 5 milliwatts, is if you shine one of these high-powered lasers up at the sky, that beam of light is very potent and it keeps traveling. Sometimes these have a range of up to 2 miles. By the time this gets to airplane height, the beam has spread out so wide that it will completely flood the cockpit of an airplane and totally blinds the pilots, which is of course super unsafe. So the FAA will track you down if you're out there, you know, smoking doobies at what's that, Oakland Beach or whatever, and you're lasering some planes or whatever. They will track you down and arrest you for doing this because it's extremely dangerous for aviation. That was a demonstration of how we can't stop the attenuation. Now, as you, of course, think about this. If you take a beam of light and you spread it out, that beam is going to get weaker and weaker and more diluted. Lasers are, of course, very potent, so they can still blind a pilot, but it won't be as bright to the pilot as the brightness is on my board here, because that same amount of energy is now spread over a wider area. For the most part, when we deal with stars, we have a lucky situation, which is that do I have a ball or something? What happened to a rainbow ball? Anyways, someone was playing with that this weekend, I'm sure. I've got all sorts of ick in my mouth today. All right, so let's take this ball instead. Well, that's troubling. I don't know what happened to rainbow ball, but I'm starting to get panicky here. Okay. A star as a sphere is an isotropic emitter, and that means rays leave every point on the surface in all directions. If I were to pick a spot like this yellow spot, a beam will come perpendicular off the surface, but it also travels sideways. This whole thing is glowing in all directions. It's a nice uniform light, especially with a star. It turns out that we know a lot of things about spheres, and these things are going to come up over and over again in our class. These are things that you would have learned about in geometry, but today not everyone takes geometry, so I'll have to remind you what you didn't learn. In the case of a sphere, spheres have a volume 4/3 pi times the radius cubed. That won't be useful now, but it'll be useful later. And spheres have a surface area of 4 pi r squared. I'd like you to notice the r dependency of volume versus surface area. A volume has units of like cubic meters, so you see r is raised to the 3rd power. Surface areas have units of square meters. You'll see that r is raised to the square. And of course, if you need your picture of a sphere, it's something like this, right? When you take the surface area of a sphere, what you're doing is you're basically dividing the entire surface up into a bunch of potentially square meter panels like this. Sorry, my art skills aren't really good enough to do that right. And you're dividing it by all of the square meters, and then you're saying how much area is on one of these square meters. Imagine that instead of your sphere being a ball, your sphere is a massive sphere surrounding a star. And here I'd like to use my slideshow because the picture is a bit superior. So here's your star. You can see your different areas. The luminosity is going to be spread over an area of space that's successively bigger as you travel through space. Now, if I wanted, I can think, this is a little bit abstract. I can think of this distance here as the radius of a massive fucking sphere, or I could think of this as the distance between me, the observer, and usually the observer is, you know, here or wherever sphere you're at. The star is there. So you can also kind of think of this as the distance between you and the star. You'll remember that, so basically what I'm saying is you can kind of use the inverse square law in one of two ways. And since I know I'm going to ask you multiple questions on the test, it seemed fair to really drive this home again and make you try a practice problem. For the inverse square law, we could calculate the brightness at the surface of a star. In that case, we would substitute in for the area 4 pi r squared, luminosity over 4 pi r squared. That's when you want to find the brightness of light coming out of the surface of the sun. On the other hand, I could also try to calculate the brightness of a star on the sky. And what that means is you're really asking, how bright is that little pinprick of light that's 25, 30, 100 light years away? In that case, it's better to think of the radius of the sphere as a distance, with you, the observer, here, and the star over here. And then the inverse square law can look like this: brightness over 4 pi d squared. Now, to be honest, these two formulas are the same thing, and they're modular, and they can be applied in different ways. But it turns out that when you're a newbie student of science, you tend to get really hung up on what does the D stand for? What does the R stand for? You guys want to hear that R stands for radius. You want to hear that D stands for distance. You don't want to hear that R stands for distance, so that's going to throw you off your horse, okay? In reality, R or D are just a unit of length over which you're spreading out light. But that abstraction comes with time. Enough yapping. Let's try a sample problem. You want to do that? Want to make this a little more concrete? That's a good idea. Let's imagine that we're an astronaut on a spacewalk, okay? And we're about 1 astronomical unit from the sun. So let's just call up a little picture here of a spacewalk. And let's imagine that we're installing a solar panel, and maybe we're testing it out. Could I get a solar panel spacewalk? That would be pretty cool. Oh, fuck yeah. Okay, I like these pics. They look pretty gnarly. This one I just saw. This one looks particularly nice. Suited for our purposes. Okay, so let's imagine that this solar panel is pointing directly towards the sunlight. And let's imagine that this solar panel is 1 square meter. That is, it is 1 meter tall and 1 meter wide. Basically the size of my dry erase board. I want to know, what is the brightness of the sun at a solar panel 1 astronomical unit away? Can I erase?
I still need it, but I'm almost done.
Go ahead. Yeah, that'll give me time to say. Actually, I'm wicked thirsty today. My throat is very dry. Let me dump some water in here. All right. You cool, Kiana?
Yep, I'm all set.
This is the type of question that I will be making you do on the test. No word of lie, something similar to this, okay? So question, find the brightness of the sun at Earth, a distance of 1 AU away. So in other words, if you were holding a solar panel towards the sun, the reason why I chose a spacewalk is it turns out that the sunlight gets absorbed partially by our atmosphere. We'll talk about the atmosphere next, but I wanted to get us above the atmosphere so that we were still 1 AU from the sun, but we didn't have anything between us and the radiation source. So obviously, here's the sun, right? And you're 1 AU away with your solar panel, and you're trying to figure out how much light is being splashed over the area, kind of like I just did with my laser. Which version of the inverse square law do I want for this problem? I guess I kind of hinted already. I shouldn't have done that. What version of the inverse square law do I want?
The second one, B equals L over 4 pi D squared. Or sorry, to the second, or is,
Sure. You can say either one, squared or to the second. What should we use for our L and our D? What is the luminosity in question here? Come on, you know this. Don't play with me.
1 AU,
Wait, that's the L?
maybe not.
The L is not 1 AU. What does L stand for? Was that Taryn? Who's talking to me?
That was Kelly.
Oh, sorry. Oh,
Or
Kelly.
is it 100 watts per joules over seconds?
Hold on a sec. 100 watts is okay. Hold on.
I'm just going based off my notes to fill
Right.
it in.
There's a bunch of units jostling around in your brain right now. 100 watts. Okay, this is actually 40 watts, but pretend. Okay. 100 watts would be typical luminosity for a light bulb. The sun has a much higher luminosity. And yes, Kelly, I was expecting you to use your notes. It's just that I wanted you to use your notes from last class to look up the luminosity of the sun.
Is it 4 times 10 to the 26?
Nice. That's a number that you're eventually going to accidentally memorize, and I wanted to get started right now. So the luminosity of the sun, notice my symbol for the sun, has a fixed value from our last lecture of 4 times 10 to the 26 watts. The distance is 1 AU. The luminosity is not 1 AU. The distance is 1 AU. But we can't use AUs here because I ain't interested in getting my brightness in watts per square AU. That would be awkward. I want watts per square meter. So what am I going to have to do?
dimensional analysis.
That's right. Okay, so Kelly, since you made the mistake of talking to me, you know, you're a troll technically, but you're a participating troll, which I appreciate. Do you want to try from your darkness there to see if you can do dimensional analysis?
I can try, but what are we converting it to again? I didn't hear you guys.
Well, if we were to use why don't you try to figure it out, which is even more useful. Like we're on the test, you'd have to figure it out. We want to use MKS units. I'll give you a hint, and I'll tell you that watts are MKS because they're joules per second. So watts are totally good for brightness. AUs are not MKS. What are our MKS units of distance? Can you remember? Here's a hint. It's got something to do with M. Sneeze.
Plus,
Thank you.
No, I don't remember.
Does anyone?
Kilometers?
No.
Meters then?
Yeah. MK. All right, Kelly, you need to write this down. This matters for your test. MKS. Meters, kilograms, seconds. You need to know MKS because most of your units need to be converted there. Okay, Kelly, now it's time for you to convert 1 AU into MKS. Now, did you get the formula sheet that I sent the class?
I wrote everything down that I watched your notes, but I didn't get anything that you sent.
Well,
Like
I emailed that formula sheet to everyone.
Okay, then I didn't check my email yet.
Well, you're on your computer. Do you want to click it?
Yeah.
Or I can look it up again and try to send it to you again. Because we have to pretend like this is the test, right? There's no more fucking around. We got to get serious. I'm worried that you guys are going to be flapping in the breeze here. Here's my midterm formula sheet. Let me see if I go to the chat window. I think I can file drop this right to the whole bloody class. CCRI. I can't find it. All right, here we go. Look, boom. Check your chat log. I sent it to you. So what I was hoping you'd do is I was hoping you'd look up what an AU is. This is how you would do it on the test. You'd go and you'd say, let me, wait, can you guys see my screen? Yes or no? Am I sharing my screen?
No.
Shoot. Share screen. Share. I was hoping you'd go to your formula sheet and you'd look up, all right, 1 AU is 150 million kilometers. I see that. All right. So let's start there. Start there. What are you going to do, Kelly?
So you're gonna put 1 AU times.
Why don't we start? I'm
division-
gonna save you a little bit of time. Let's start with 150 million kilometers. Okay. We could convert from kilometers to AU, but I kind of just did that.
Okay, so 150.
So pretend this is your starting point. This is step 1. Write down what you want to convert with its units. Step 1.
Then we multiply it, make the division line.
Okay.
You put kilometers on the bottom,
Correct.
and then seconds on top.
Wait. You can't convert from kilometers to seconds.
Oh,
That's like converting
put-
from bunnies to pineapples. It don't make no sense.
Meters on top.
That's right.
Yeah.
They're both units of length. Okay. Okay. So now your kilometers cancel. Then what?
And then I suck at figuring out how many meters is in a kilometer, so I have to.
Well,
like,
luckily you don't have to. You don't have
go
to
back to my notes to.
No. Just use the formula sheet, kiddo. That's so I have to teach you how to use your formula. I gave you everything you needed to know right here.
Oh, okay. So 1 kilometer equals 1,000 meters. So you put 1,000 on top and 1 on the bottom.
Okay. Good. And now you can do it in your head or you can do it with the calculator.
Probably with the calculator.
No, probably your head. What's 6 plus 3?
8.
Wait, try that again. 6 plus 3.
Oh, sorry, 9.
All right, okay. 6 plus 3 is 9. So we have 150 times 10 to the 9 meters. That's it. All right. Now, if you put it into your calculator, it's going to say 1.5 times 10 to the 11 meters. Same thing. All right. Now we plug it in, guys. Brightness is luminosity 4 times 10 to the 26 watts over 4 times pi times 150 billion meters squared. You're not done yet. You can still screw this up. Trust me, you could screw up anything. So punch this into your calculator and see if you get the right answer. I think I'm going to start timing you guys in your calculations using magnetic sand. Oh, wow. this even sticks to my laptop. That's dope. Woo! That's creating some waves there. Okay. I guess there's limits here to what I can do. It's too bad you can't see this, but it's actually really cool. Let me autofocus this. All right. You guys should be done your calculation by the time this magnetic sand runs out. Okay, time's up. What'd you get? Something went wrong, Taryn. You did it bad. I know what you did too. Taryn, I can already tell you, Mateus got it. Taryn, let me tell you what you did so that you don't do that again. You hit times there, and you hit times there, and that's not going to get you the right answer. You've got to hit divide and divide. Otherwise, the calculator doesn't know those numbers are on the bottom. So try it again. You got it, Andrew. Who else? Sorry, Mariah, you did the same thing Taryn did. You hit times instead of divide. Nick, you hit times instead of divide.
But I don't know what I'm doing wrong.
You hit divide? Did you forget to square your distance? Oh, did you forget to hit equals? Sorry, Kiana, no good.
No, I definitely forgot to square my distance. Thank you.
Okay. Kiana, you did something wrong too. You got it now, Taryn. Very good. Kiana, Nick, you want to see if you can clean that up? Who else had a weird one? Mia, did you have a weird one? Oof. No bueno. What are you typing? Yeah, you got it, Mariah. Sorry, Nick. Okay. I think we better just watch me, okay? Because something weird's happening. Where is my buddy here? Where's little buddy? Let's try this one. Harsh. Okay, you ready? Watch. 4E26 divided by 4 divided by pi divided by 150 exp9, square that dude, and then equals. Did it work now?
I'm making the rookie mistake of multiplying by 10 and then adding the exp 26.
Oh, what the hell?
Yeah,
We're way past
rookie
that.
mistake.
Just exp.
Rookie mistake.
Yeah, rookie mistake. There is no more times 10 in this class. There's no more time. There's only exp.
I accidentally put the parentheses in.
Okay, so I tried to say this before, but maybe wait. Who said that with the parentheses? Who was?
Kelly.
Oh, Kelly.
Because
Kelly,
I know sometimes we do that, so I wasn't sure.
we hardly ever actually type parentheses. The reason for the parentheses isn't about the calculator, Kelly. It's about the fact that the square has to distribute to the number and to the units. You see, Kelly, if I were to write 150 billion meters squared, a reader might not know if I just meant 150 billion square meters or 150 billion meters square thereof. Do you see the ambiguity?
Yeah.
So it's there for bookkeeping, for units. It's
Okay.
not for the calculator.
Okay.
By the way, it should not have screwed you up if you used the units, the parentheses correctly. But every time I give you guys another key to press, danger, danger, you know? So, okay, Taryn, if you're still there, let me find your little face. There you are. Taryn, I thought maybe since you had it earlier, you could try to round that for me. Let's hear your good rounding skills.
How many sig figs do you want?
When in doubt, choose 2.
Okay. 14. Oh my gosh. Or do you want like 1.4?
No, well, the answer is definitely not 1.4, right?
Right.
I don't want it. I think what you meant when you said the 1.4 is you meant, do I want it in scientific notation? Is
Yes.
that what you meant?
Yeah.
Is the number greater than 1 million or less than 1 million?
It's less than 1 million.
Then no, I do not want scientific notation.
Okay. I'm a little bit confused. Sorry.
Well, okay. Does anyone know how to do it?
1400 watts per meter,
What did I just say about distributing that square?
meter squared.
That's right. So Taryn, I wanted you to say 1,400 or 1,400. Either one.
Okay. Yeah. Okay.
All
I
right.
was a little bit confused
Sure.
about that. but-
Or if you were really confused on how to say it, you could have said 1400.
I just didn't realize that like you needed the 2 zeros after, but now I get it.
Well, of course, this is a number of order 1,000. You can't make
Right.
like if you won $1,400 in scratch tickets and you went to the lottery store and they gave you $1.4, you wouldn't be cool with that, right? Because $1.4 is not the same as $1,400. You can never change the power of 10. You can never change the order of magnitude of a number. That is a sin. All right.
Right. Because like the answer is 1414. I wasn't sure if you wanted that or
No, the whole point of rounding is that other 14 is not real. That's just shit that your calculator spit out that has nothing to do with reality. You know what else isn't real? The 0.52619 or whatever it was that came after it. That's garbage too.
Hey,
Whatever.
Professor.
So on the test, do you want us to round or do you want us to put the exact number that we got?
Even the way you said that is offensive to me. Listen, this is not exact. You're trying to tell me, well, okay, yesterday there was a crazy person shouting about Jesus and radiation on the street with a megaphone. Just because she shouts some shit on the street with a megaphone, it doesn't mean that it's real. Just because your calculator spits some crazy numbers out, it doesn't mean that it's exact or real. These numbers are in fact lies. Just as that woman on the street was a false prophet, this is false prophet numbers here. Do you understand? You can't trust things that people say. You have to know what's real. And how do I know that the first 1 and 4 are real? Because I know that this 1 and 5 is real, and I know that that 4 is real. It's about precision. You can't get a more precise number out of your calculation than you put into your calculation. And you put some shitty numbers into your calculation. These are low-grade numbers. These are McDonald's chicken nugget numbers, okay? That's what you're dealing with there. So you get a McDonald's chicken nugget answer. This exact is not actually exact because it's fake. I want you to understand that. These numbers don't mean anything. My answer on the test will be A, 1,400, B, 6,000, D, 1,900, or you know what I mean? Like it's there that you have to round. You have no choice. And I know you guys are bad at that. That's why we're practicing.
Professor.
This is a very famous number in astroengineering. This number is known as the Solar Irradiance. It has its own name. The solar irradiance is the maximum amount of energy that you can get on a solar panel from space. And once that comes down through our atmosphere, guess what it's reduced to? So here's your atmosphere, and here's the ground. By the time that light gets down to the ground, it's been reduced to 400 watts per meter squared. So your atmosphere absorbs roughly 2/3 of the sunlight, or it's actually backscattering it, but some of it is absorption. So the best, if you get solar panels on your house on a perfectly sunny day pointed directly at the sun, the best you can get is 400 watts per square meter, which is actually still plenty of energy. If you have 2 solar panels, you get 800 watts. If you have, 10 solar panels, then you get 4,000 watts. And 4,000 watts is enough to power your guitar amplifier. Okay, so that's cool. You can rock out just from sunlight.
Professor.
Yes,
I have a quick question.
sure.
Is there any way that you could just punch that calculation into the calculator one more time. I'm just comparing how it's supposed to be done versus how I'm doing it so I can see what I'm doing wrong.
I'd love to help. So the sun's luminosity is 4 exp 26 divide by 4 divide by pi divide by 150 exp 9 squared equals.
Yeah, I see what I did wrong. For this one, I didn't add pi in, and that's why I kept getting a weird number. That was the only thing I didn't do was the pi part.
I preferred if you said multiply pi in, but okay. Yeah. Hold on, I've got the sniffles here today. Excuse me, my nose is a tickling. This is burning up a lot more class time than I intended, but could we try one more sample problem? I think that would be a good idea. You agree, Mateus? This is how we would calculate the brightness of a star in our sky. Most brightnesses of stars are going to be way, way, way lower than that. They're going to be really tiny. Here's another idea. Question. Find the brightness at the surface of the sun. The sun has a radius of 700,000 kilometers. The sun has a luminosity of 4 times 10 to the 26 watts. Okay, what do I do? Which formula do I choose?
B equals L over F pi r squared.
F. Where do you see F?
Did I say F? I meant 4 pi. Sorry.
It sounded like you said F, but whatever. I could be hearing things. Okay, what are you going to do about the R? Can we just do a little more fortissimo, a little less allegrando?
We have
Dimensional
to convert it
analysis.
to meters.
All right, so I don't have time for you guys to do that. So 1,000 meters per 1 kilometer is 7 times 10 to the 8 meters. Okay, let's plug it in. 4 times 10 to the 26 watts over 4 over pi over 7 times 10 to the 8 meters squared. Punch them up. I should do push-ups every time I wait for you guys to calculate. I'd probably get really buff if I did that. Okay, Kiana, tell me how, actually, Taryn, Kiana, you got it right. Taryn, you got it right. Taryn, why don't you try to round that for me? Yeah, are you feeling good about that, Kiana? Yes, you are.
Yeah, I'm so surprised I got it right.
You know what? That means this time that I've spent is worth it. Nice job, Mia. Very good. Taryn, why don't you try rounding that again? Show me you do better this time.
Okay, so since it's more than 1 million,
Scientific notation. Good,
Yep.
Andy. Looks good, Andy.
1, 2,
Amy, how you doing? I gotta check
I
your
was gonna say 6.5 times 10 to the 7th.
Excellent. Now, yes, that's probably how it would be written. Oh, wait, what are the units?
Meters.
Careful. Meters are on the bottom. Meters are being squared, and you still have watts up there.
Oh, okay.
This is a
So,
brightness, after all.
so then it would be watts divided by meter square.
That's right. Watts per square meter. By the way, a classier way to do it, this is perfectly acceptable, Taryn, but even classier would have been to move the decimal place back once and write it as 65 million watts per meter squared.
Can you show me the calculation on that? Because I got something like 1.68.
What's
Okay,
your
did the
power? That tells me what you did wrong. What's your-
Negative 17.
You hit a funky button, but I'll show you how. You with me, Sabrina?
Mhm.
Was that
Right.
Sabrina?
Yep, it is.
4e26
Mhm.
divided by 4
Mhm.
divided by pi
Mhm.
divided by 7exp8. Oh, you probably forgot to square that and then hit equals.
Yeah. I don't know what the hell I did wrong, but okay.
Whatever you
Yeah.
did, don't do that again.
Okay. All right.
Did you get it now?
Yeah, I did. I did.
All right, cool. Well, several questions on the test are going to be based on this formula. So I knew you guys were going to be struggling. It didn't seem right to not waste some time doing this. All right, let's return to some different stuff now. Tell me about the 3 types of spectra we find in nature. If I take a spectroscope, if I take a prism, and I break some light apart, what type of spectra will I discover from glowing objects? Does anyone understand what the fuck I just said? Because I'm starting to think.
Photons?
Photons are particles of light.
Are you referring to that diagram you showed us with that little window of what we could see?
That's the electromagnetics. Hold on, wait. Can you say that again, Kiana? I'm not sure I understood what you were referring to.
The diagram that you showed us with the what our eyes can actually like pick up, and it showed like a little diagram of just what we can see out of this whole bar. I just didn't know if
Okay.
that's what you were talking about.
You're referring to the electromagnetic spectrum, 65 versus 63, function F5. This is the electromagnetic spectrum. This is all the different types of light that exist in nature, okay? But I'm not asking about that. I mean, this is all the different types of light you can find. But when you go out and you break light into a spectrum, it does not always look like a pure rainbow. It can look one of 3 ways. And you have to know those 3 ways for the test. It can look like this, it can look like this, or it can look like that. And I want to know the names of these spectra, because without it, you can't learn astronomy.
The continuous one is the rainbow one.
Good. So this is continuous. What else?
The emission line spectrum,
This is emission. And the third one?
absorption line spectrum.
Good. Fine. I accept. What about this light bulb? Can I do this? Oh, I just bought a, hold on, I just bought an extension cord. Shit, what did I do with that thing? I keep needing an extension cord, so I bought an extension cord. And where? Ah, here it is. All right. Why even tell when you can show? What type of spectrum will I find if I put the spectroscope on this?
Continuous?
That's right. Can I do this? pretty fucking cool if I could. Wow. Ooh, who's cooler than me? Right you are, sir. Wait, hold on. Yeah, look at that. A beautiful rainbow, perfectly continuous. That was fun. Okay. What's glowing? What causes this to glow?
Light.
Well, light is what comes out. Light is the glow.
Is it the luminosity?
The luminosity is the total light that it puts out. But that's not.
Black bodies.
This is a black body. This is the part of the light that glows. What is that stuff? That's a special
Is
type
that
of metal.
brightness? Oh,
Pardon?
I said brightness, but I'm assuming it's not.
No, brightness is how much your eyeballs detect. Luminosity is the total light that this puts out in all directions. I'm
Okay.
asking a totally different question. I'm asking what the shit is this metal?
Is it lead?
No, it's
No.
tungsten. Tungsten. They call it a tungsten filament. 73. Lead could actually probably be used in its place, but lead is either toxic or it's, I don't know, maybe it's more expensive. No, tungsten's wicked expensive. Do you want to know why they use tungsten? Let me show you where tungsten is on the periodic table of the elements. Tungsten is a rare metal with 74 protons and 110 or 13 neutrons or something. And one of the reasons why they use tungsten is because you need to make that metal really, really hot in order for it to glow. And at the temperatures you require, most metals would actually vaporize. Tungsten. Let's learn about.
Wait, you said it was rare, right? This metal.
Oh, it's expensive, anyways. Yeah, it's.
Oh, okay. Because I was about to be like, if it's rare, then why are we mass producing light bulbs if it's so rare? But if
Well,
it's
you
just-
only use a tiny, tiny amount because you don't have a choice because you need light. You're only using a tiny amount of that metal. It has a super, super high melting point and boiling point. Its melting point is around 4,000 Kelvin. Its boiling point is around 6,000 Kelvin. One of the reasons you don't expose it to air, the reason why it has to be in a partial vacuum, is so that the air doesn't heat up and either catch fire or B, just melt the metal. The metal will melt, but if it's in a vacuum, it has to sublimate to gas, and that makes its melting point or its boiling point even higher. So I don't think you can heat copper up to that temperature without it just melting. The temperature of a typical filament is around 3,500 Kelvin. So let's talk about a tungsten filament. It has a temperature of 3,500 Kelvin. I'd like to know the answer to two questions here. How much light does it emit? And two, what is the peak wavelength of light emitted? These are also questions I will be asking you on the test next week. These are questions you have to know the answer to be able to understand astronomy. Do you guys know how to solve these questions? What would you do? Let's look around our formula sheet here. We have to do this fast because I'm totally wasting this. I'm screwing up this class every day. I don't know how I'm doing that. Can you see any formulas that might be useful for answering that question?
Stephan-Boltzman?
Nice. Very good, Mateus. Which question would you use the Stefan-Boltzmann law for?
The first one? Well, can you go back to the questions actually?
Yeah.
Yeah, the first one.
Okay. I like your moves. So let's use the Stefan-Boltzmann law. Brightness is sigma t to the fourth, where sigma is the Stefan-Boltzmann constant, 6 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. Six times 10 to the minus 8 watts per meter squared per Kelvin to the fourth times 3,500 Kelvin to the fourth power. Okay, do it. Punch them up.
Nine times 10 to the 6.
Units?
Ooh. Is it watts per second? No.
Do your unit balancing, Mateus.
Watts per meter squared.
That's right, because Kelvin to the fourth cancels with Kelvin to the fourth. This is telling you the brightness of the filament. If you look at my light bulb here, this is an appliance bulb. You replace your stove or your refrigerator light with this. This light bulb has a luminosity of 40 watts. I have a riddle for you guys. If the bulb has a luminosity of 40 watts, how could I have just calculated that that bulb is emitting 9 million watts per meter squared? That is my riddle for you guys. How can a bulb that emits 9 million watts per square meter only have a total luminosity of 40 watts? Those two numbers don't seem to connect to each other. I wish I had saved a broken light bulb here.
I can't see the bottom.
Sorry. I was thinking that some intrepid student out there might be, this is a hard question. That's why I'm asking you the tough questions here. How can a bulb emit 40 watts and also 9 million watts per meter squared at the same time? That doesn't
We
seem
need
to make-
Vladimir. He's not here.
We do need Vladimir. Vladimir, if you're watching this later, see if you can answer that question. Vladimir seems like he's got some training in physics or maybe mathematics or something. And one thing that comes with taking a few physics classes is you learn to start thinking in terms of units. Units tell you what's going on. The secret to this question is 1 in the units and 2 in the discussion that we had earlier about brightness versus luminosity. They measure different things. Damn. Okay. 9 million watts per square meter means at this temperature, your metal will emit that many watts per square meter of metal. Now, look at this little dinky thing in there. Geez, you can't even see it without me focusing. Look at your filament. How close can I get this? Look at that thing. Imagine breaking the glass, pulling out the tungsten, taking a little ball-peen hammer and just smashing it into a little sheet. Would that sheet cover my entire board? Obviously
No.
not.
No.
You don't have a square meter worth of metal in there, right? The surface area of this thing is so microscopic. Let me put it a different way. Suppose I could buy from some industrial company a full square meter worth of tungsten. It would probably cost like $1 million or something outrageous. I wonder if I could, I'm assuming that it's expensive, but what the shit do I know? You know, there are limits. What if I, just for fun, just to keep the day fresh, the price of tungsten. Could I just look that up? $270 per metric ton. That is a lot of metal, though. A metric ton is 1,000 kilograms. Is tungsten is less expensive than gold? Oh, shit. Okay. I guess tungsten isn't that precious. Why did I think it was? I thought it was because it was, in general, the further you down you go on the periodic table, the rarer the element is. But okay. So there's your answer of why we can pump out so many light bulbs. Do you understand the riddle now? The luminosity depends upon the geometry of the object. The brightness depends upon the temperature. There's a difference. This is why you solve the Stefan-Boltzmann law for brightness, because you don't know necessarily how many square meters of the metal you have. Okay, let me actually, wait, test. Let's do a test to see if you understand. Let me show you the steel ingot in a forge picture again. Remember this one? Images. Come on, baby. I'm so running out of time and I'm terrified. Okay. I don't know what the luminosity of this glowing block is, but let's pretend this thing pumps. That's probably about the brightness of a standard light bulb or more. Let's say this thing pumps out a total luminosity of 100 watts. Here's what I want you to imagine, guys. If I took a second identical block of metal and I stacked it on top, would the luminosity of the total system change? Would the brightness change? Would they go up or down? So I want you to imagine that I took an identical block and I laid it down on top of it. Would the luminosity change or would the brightness change?
The brightness would change.
False.
Damn it.
Would the luminosity change because of how much more metal is there?
Right. In other words, this thing's already pumping out 100 watts in all directions. Add another one, and now you're pumping out 200 watts in all directions. The reason why the brightness doesn't change, Maria, is because brightness is measured per square meter or per square centimeter. Brightness only depends upon temperature because for a standard little chip of metal or a little square of metal, the temperature tells you how much light is emitted. You see? I don't know, I'm trying here. Okay, now let's ask another question. What if we asked about the color emitted? And to do this, oh, Jesus Christ, I'm so running out of time. Okay, the question I'm trying to ask is, when you look at this rainbow And here it's kind of tough because the camera doesn't show it to you perfectly. The camera distorts the colors a wee bit. Are all of these colors emitted with the same intensity, or are some colors brighter than others? What do you think?
They all look kind of like the same intensity to me.
I think it's because of the camera kind of messes that up.
I mean, if anything, the green color looked a tiny bit brighter, so maybe, you know, they're not all the same because of that, but they relatively look all the same though.
Yeah, the camera distorts a bit. There's a reason why the green might look a little brighter as well. Why don't we calculate it, and then we will discuss it, okay? Let's answer questions. So I want you to presume that although they did look the same brightness, because unfortunately we're doing remote learning right now, let me just be very clear about the question I'm asking here so that you understand before we solve it. The question I was asking is, if I took that rainbow and then I took a light meter and I just scanned along the spectrum, asking how bright in watts per square meter is each color, I'm trying to find out if one of these colors is emitted more than the other. Kiana, if that was Kiana, she suspects that perhaps the green is a bit brighter than the rest. There's a formula to calculate this. Do you know what it is?
Wien's law.
That's right. So for question 2, Wien's law. Or if you're German, you might say Wien's law. So lambda max is 3 million. The units are nanometers times Kelvin. Those aren't variables, those are just units. Divided by the temperature. And I want you guys to plug in 3,500 Kelvin. And I want you to tell me what you get. Sorry. I went to a video game arcade on Sunday, and that was very, very naughty of me. I don't know what I was thinking.
$850 nanometers.
Okay, good. Now, here's the kind of question I'm going to be asking you on the test as a follow-up. Once you calculate the peak wavelength, I'm going to ask the question, in what regime of the electromagnetic spectrum is this light found? Can you guys answer that question? In what regime of the electromagnetic spectrum is this light found?
Infrared.
Very good. Can you just explain how you knew that to everyone else in case they didn't follow your logic, Mateus?
I actually looked it up. Above 700 nanometers is infrared.
Yeah. Let's just do what he did. I just want everyone to follow in his footsteps here. He said, okay, it looks like 700 is kind of red, and that puts 850 right about here. In a way, it was a trick question, guys. The peak wavelength emitted by that bulb isn't even in the visible spectrum. It pumps out most of its light in the infrared. Let's imagine that you could make a plot of brightness versus wavelength. What would it look like for a black body? I want to, first of all, does everyone have this? Because I need to erase.
I still need it.
All right, Andy, let me know when you're done. This is garbage. Just total garbage. This stuff is really helpful for you guys. You know what? I know all of these exercises are really going to help prepare you for the test. So I did you a good thing today, but I did you a bad thing because I had new material to cover and I'm kind of not doing it. All of this was stuff I needed to fix from our previous lectures.
All right, I'm all set.
All right. I want you guys to work with me. Let's take a black body. So this is what is known as a black body profile spectrum. For anyone in the audience who has some physics background, who has aspirations to study such things, it's also known to physicists as the Planck function. But that's advanced, so you don't need to know that. What it is it's a famous plot of brightness versus wavelength for a black body at some random temperature T, which you have to select beforehand. I'm going to try to draw one for a 3,500 Kelvin black body. In other words, one that's appropriate for a tungsten filament light bulb. So on this axis, the y-axis, I will plot the brightness in watts per meter squared. On this axis, I will plot the wavelength in nanometers. But I won't simply plot visible light. I'm going to plot the whole damn thing. So I had a purple marker at some point. Where's that purple? Where's that purple? Here it is. Okay. So over here, I'll do violet at 400 nanometers. Okay. And over here, I'm going to do red at 700 nanometers. But I'm also going to plot all of the wavelengths of the EM spectrum. I'm going to plot infrared. Radio is even longer. I'm even going to plot some UV and some X-rays. Hell, I'll even plot those Teenage Mutant Ninja Gamma rays. Okay. The first question I have is for Kiana, actually. Kiana, here's a question. Suppose you had been right. And you're actually, so you said green eventually, but at first when we were talking, Kiana, you said it kind of, just to be honest, looks like all the colors have the same intensity. And I believe that was partly an artifact of the fact that you weren't looking at them directly, but you were seeing them through the camera, right? But Kiana, suppose you were right, and suppose all of the different colors did have the same brightness. Can you tell me what the plot would look like?
Would it just be like maybe a bar going straight across, or like
Yes.
something linear like that, because it's all the same?
Yeah, well, linear could be up or down, but you were first correct.
Yeah.
It would be a horizontal bar, because for every color, whatever that color was, you'd have the same exact intensity, which would be this number, whatever that number is, okay? In reality, nature does not do that. And there was a group of scientists in the late 1800s and early 1900s who were just obsessed with trying to figure out how temperature changed light. They realized, like Kirchhoff did, that once you had a compact metal, it didn't matter if the metal was made of steel or copper or tungsten, they all kind of glowed in the same way, and it only depended upon their temperature. One of the problems with studying these metals using a spectroscope is a typical object, like let's take, here's a lump of iron. It's a meteorite, but it's a lump of iron. If I put this in a furnace, it would eventually get warm enough to glow like a hot rock. And the problem with trying to analyze light coming from this rock is some of the light would be radiated based on the temperature, but some of the light would be scattered from the surface from light that's around the room. And they didn't want the scattered light to contaminate their results. They tried to invent what they called a blackbody. A blackbody would be a substance that was so dark, so black, that no photons that hit its surface could even bounce off of it. And it would only glow due to its temperature alone. And they realized they couldn't quite make something like that. So here's what they did in their insanity to discover the true blackbody. They actually built an iron cavity, a giant cylinder made of iron, and they heated it up so that the interior walls of the cavity would glow. And they knew this would be a perfect blackbody because it was sealed from the outside, so no light could get in. Only light could be generated by temperature. Now, of course, the trick was they had to observe it somehow. So they took a drill and they drilled a little tiny hole in the cylinder, and they put a quartz window in it. And then they put a spectroscope up to it, and they analyzed the light. And here's what they discovered about the brightness as a function of wavelength. It had a particular function, a particular shape that we now call a blackbody profile spectrum, and it's unique to blackbody. It's unique to light. It looks something like this, like a bell curve that's lopsided. My bell curve could have even been more lopsided, actually. Let me see if I can do that better. It's like something like that. So the takeaway from this graph is this is not a discontinuity. It's supposed to be continuous. The takeaway from this is twofold. And I want to talk about, I'm going to have to erase up here to explain the takeaway. There are two takeaways from this. The first is black bodies emit all wavelengths of light. And that means no matter what wavelength I go to, I can find some radiation coming out of it. For instance, if you said, does this blackbody emit purple light? Well, first of all, you could see that it does, but you can also see here, yes, I'm getting some purple light. Does this blackbody emit some red light? Yes, I'm getting quite a bit of red light. Is it emitting ultraviolet? Yes, UV. You know what this even suggests to us, students, which is crazy? This thing is even emitting a very small amount of gamma rays. Must come from this. Although the flux of gamma rays is so pitifully small that you don't need to worry about it turning you into a mutant Ninja Turtle. The second takeaway is that not all wavelengths are emitted equally, that there is a peak wavelength, which in our class we call lambda max, which is emitted greater than any other. And that is the wavelength that you just calculated. For a 3500 Kelvin bulb, that wavelength peaks in the infrared. And have you guys ever put your hand up to one of these tungsten filament? I mean, you kids are so young, you might not have even grown up with these things, but I grew up with this as a kid, right? And if you put your hand up to this thing, you feel some crazy ass heat coming off that. That heat that you feel is infrared photons hitting your hand. It's not the air, it's infrared light. Notice when you get close to it, it gets wicked, wicked hot. That's the inverse square law that's going on there. Why the fuck would you want to spend money on a light bulb that pumps out the greatest amount of light in a wavelength that your eyes can't see? I mean, consider what a hideous waste it is. Let me show you a more professional version of the blackbody curve that we just drew. It's actually a family of curves that depends upon temperature. The one that we just drew is this one here, which is appropriate for about a 4000 Kelvin blackbody. If you think about the total 100 watts of a typical tungsten bulb, most of those 100 watts are pumped out here in the infrared, and only a small fraction of them are pumped into the visible. This is why today, when we go and buy those LED lamps, have you ever noticed you don't need the wattage to be as bright? Like for LED bulb, the equivalent of a 100-watt bulb is like a 35-watt bulb, right? That's because those LED bulbs are not using blackbody light. They're using the law of emission. What they're doing is they're using quantum light emitting diodes, LEDs that pump out green light, red light, and blue light, and they're mixing them together. And you've probably seen LEDs on the side of R2-D2, or, you know, you guys know what an LED is, I'm sure, right? LED light. Basically, they've created ones, you know, so for years we had LEDs that could create red and we could create green LEDs, but we couldn't figure out a way to use the law of emission to produce a blue LED. And when they figured that out about 10 years ago, the person who did it, they won the Nobel Prize in physics. Because think about the fucking implications of this, right? Suddenly you can mix equal parts red, green, blue. You have a source of pure white light that takes way less energy. Not only are you saving tons of money in your home, but you're saving the damn planet in terms of your energy usage and climate change. So LEDs take all of the money in dollars and cents that you're putting into your lamp, and they're pumping it into a portion of the spectrum that you need for your eyes. Plus, you're not heating up your home, which, although it might be nice in the winter, is not helpful in the summer, right? Stars act more like black bodies. They pump out light in all parts of the spectrum, and we're going to be studying that aspect of them. Where am I here? Oh, okay. I had some new formulas to get to. I think I'm going to have to extend this into Thursday's lecture. And I'm really not happy. Oh, one last question, and then we'll pause for tea break. Why do you think human eyes, if you've got a whole electromagnetic spectrum to work with, why did our eyes develop to see between wavelengths of 4 and 700? Why not have eyeballs that see at radio wavelengths? Why not have X-ray specs built into our heads? Do you know that some animals do? For instance, let's consider the pit viper. Din, 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 din. Pit vipers are a type of snake that have developed not only so these eyeballs are visible light eyeballs. They see at the same 400 to 700 nanometers that we do. Why the pupils are shaped as a slit, I'll tell you about next class. But do you see these things that you probably thought were nostrils? They're not nostrils. This is a second set of eyeballs. They're infrared detectors.
So these snakes technically have 4 eyes.
Yeah. They
That's
have
pretty cool.
4 eyes, and 2 of them are infrared eyes. It turns out that people, in a way, and little mice in the dark, or whatever the hell those things eat, mammals are like little black bodies. Do you know that you actually glow? You just don't glow at visible wavelengths. But your temperature, 99 degrees Fahrenheit, is 300 Kelvin. And you're actually pumping out infrared light. That's how you see people using those night vision goggles. For instance, here's a NASA picture of an infrared image of a man. This is if you look at a man, and this is I love this picture. It's like, whoa. Okay, so this shows you color-coded intensity of infrared emission, probably close to 10 microns. Where do you see the man giving off the greatest amount of light?
Near his head.
Isn't that cool? This is literally the brightest part of your body. The brain is a very energy-intensive organ. Notice at the extremities, you see less temperature and less light in the infrared being emitted. Snakes have developed a second set of eyes so they can see this stuff. That could have been useful for us to see people in the dark. Why didn't we do that? The answer has to do with a property of Earth itself. Our atmosphere is not uniformly transparent to all electromagnetic rays of light. This picture, called the transmission of Earth's atmosphere, shows you that our atmosphere blocks almost all gamma rays and X-rays. A little bit of UV light does get to the ground. That's what gives you a sunburn at the beach. But a lot of the ultraviolet is blocked by ozone. Our atmosphere is like transparent glass from 400 to 700 nanometers. And infrared, microwaves, okay, radio is kind of transparent too. But the sun puts out a lot more light from 400 to 700 nanometers than in the radio. So your eyes evolutionarily adapted to see those wavelengths of light that the air is transparent to. Otherwise, you wouldn't even be able to see me from this camera to here because the air would be opaque to other wavelengths of light. Snakes can cheat a little bit and see it infrared because a little bit of the air is transparent to infrared and they don't have to go too far into it. Something like that. All right. I don't have time for anything more than that. During our labs today, you know, I have a lab on the inverse square law that I would love to do with you guys. But every time I've tried to run it, it comes into problems because I can't make my light enough of a point source. It would have tied in beautifully with our lecture today. I also have
Do
a
we need to
lab.
print anything out for the lab?
Shit, I have to decide right now. Yes. Let me see how sunny it is. That's going to affect my decision. Okay. I didn't practice the inverse square law, so if I try to run it and it goes bad, then time is a factor. I can't afford that. We're going to do lenses and telescopes, which is an equally cool lab. You're going to love it. It just doesn't tie into our lecture quite as perfectly today. That's all right. Fuck it. Let's go ahead and find what you need to print. Go to your lenses and telescopes lab here. In this PDF, I just need one page. Let's see what I gave you. This is the, these 2 pages. So print those 2 pages. We might not end up using the second page. We'll see how fast we go. I'm going to print mine right now. So print this page and that page, okay? Let's take a 15-minute break, and then I'll see you guys just before 2 o'clock, okay? Deal? All right. See you guys in a little bit. Okay, Astronomy 1020, got a surprise for you. Today, we are going to be doing a slightly alternate lab. I said lenses and telescopes. I changed my mind during tea break, and now we're going to be doing the inverse square law because that's what our lecture was on today. So here's what I need you guys to do. In a moment, when I'm done with this lecture, I am going to attach this file, which has a graph and it has a table of distances. And I'm going to attach it to lab number 6. So I'll rename this something else. I don't want to fiddle around too much right now, but I'll build an assignment. Here I go. And I'll fix this up later, but it'll say lab 6 inverse square law. And I am going to attach the inverse square law files that I've sent to the students who are in the live session. So there's going to be a PDF, and there's also going to be a dot document. You can use either one. The only issue is, all right, so 10 points and unlimited attempts. Okay, there, boom. So this will be present when you guys watch the video a little later on. I want to show you what I did to the document that I printed out here. As I explained to the students, the original document had us start at a distance of 30 centimeters. I changed it so that the first distance was 10 centimeters, 20 centimeters, 30, 40, 50, 60, 70, 80, 90. If you're using the PDF, like a couple of the students, you may have to rename that yourself on the paper. Okay, here's our goal. Our goal is to investigate the inverse square law. And if you remember, the inverse square law looks something like, let me just do this here, like this. It looks like the brightness is equal to the luminosity over 4 pi times the distance squared. Now, the idea is that the intensity, sometimes we call brightness intensity instead of brightness. The idea is that the intensity of light is inversely proportional to the square of the distance. And what that means is if you double the distance, the intensity should drop by a factor of 1/4. If you triple the distance, the intensity should drop by a factor of 1/9. And that means basically that a beam of light spreads out as it travels through space, and it attenuates or gets weaker. This was part of our lecture today, and is why I was so hell-bent on changing the lab last minute, is I basically wanted to see if we could create today's lecture in experimental form. I will warn you that I've had mixed success with this before, and this could end up being a total failure, and you guys will be here real time to watch the failure. So, and you will be failing with me, so take comfort in that. 34 shows us what we're about to do today. We're gonna have a light detector. We're gonna move it to 10 centimeters, to 20 centimeters, to 30 centimeters. And we expect that as the beam gets wider, the brightness should drop at every distance. And then we'll make a plot. And I don't know if you guys know your mathematics well, if you had an algebra class, but when I took algebra, they taught me that the graph of 1 divided by x squared looked something like this. Oh, sorry, mouse pad issues. It looks like kind of an asymptote that kind of drops off like so, right? So we're going to plot the intensity as a function of distance, and we're going to see if we get that 1/x² plot. That will mean that the inverse square law is working here in our laboratory. So let me try to show you the setup now. And I'm going to use my phone for that. And the data collection is going to take all of 5 minutes. So I know I forced these guys to wait a little bit, but it won't be so bad. Share screen, iPhone, share. All right. It's loading. And camera view. Okay. So let's check out our experimental setup. I've got some lamp, but I can't just measure the brightness of intensity from the lamp, because the lamp will have some large angular size and it will create rays of different geometries. In order to reproduce the inverse square law, you need to make it so that you have this kind of artificial star, and that little pinhole there, can you see that? It's like a little artificial star that's generating some light. This little hot dog looking thing that I've constructed is a light detector. For some reason, their light detector is like this long dorky tube. So I kind of put it in this styrofoam hot dog so that I could hold it with my 1970s optical bench clamp. I have an optical bench where I can measure the distance and I can slide this thing along. And then we're going to be reading out the intensity of light in a unit that's called lux. Now, do you guys remember what units we used for brightness in our lecture today? What were the units of brightness, like when we did the solar intensity? Does anyone
Watts
know
per meter
anything?
squared?
That's right. We used watts per meter squared. Now, watts per meter squared are covering the entire electromagnetic spectrum. Lux is basically watts per meter squared, but just restricted to the visual domain. So it kind of follows the power pattern of the human eye. Remember, someone, I don't know if it was Taryn or someone asked me, how does the human eye detect light? And we learned that it detects green, red, and blue with different sensitivities. Lux is basically the intensity of light as seen by the human eye, but it's very closely related to watts per meter squared. I encourage you to look the Wikipedia page up for further details. Okay. What we're going to do is we're going to measure the illumination at all these different distances, but there's just a little more to it. And let's take a look at my paper here to understand why. I've got myself a light source, and the light source is coming from a little pinhole. let's call that the source. And then here's my little hot dog detector that looks like so. And I'm going to be trying to measure distances d and measuring the brightness in a unit called lux. The problem is it's not perfectly dark in my apartment. There's light coming from all kinds of things, right? So rather than try to turn everything off and get pitch dark, which will be difficult, we can reason that the background should kind of stay the same and it's kind of uniform and it's coming from all directions, right? So what I'm going to do is every time I take a reading, I'm first going to turn the lamp on. And when I turn the lamp on, I'll be getting rays of light from the source, but I should also be getting rays of light from the background. So with lamp on, the reading that I collect is source plus background. Then what I will do is awkwardly unplug it. I will turn the lamp off, and I will just get a background. And then source minus background gives us the source. Does that make sense? Seems easy enough, right? And it should be. Okay, my meter reads to the nearest 1/10 of a lux, but we're going to round to the nearest lux because it's a bit stabler. So right now, I've tried to match my detector up to the 0 centimeter line as best I could. You guys can see that I'm at a distance of 10 centimeters from the little pinhole, which I tried to put as close as possible to 0 centimeters. Currently, the reading is fluctuating a little bit, but we want to measure to the nearest lux. So what value shall we choose?
Well, that's hard. I would
Right.
say there 6.610,
Well, this is a number of order 600, Sabrina.
610.
Okay. Yeah, I'd say it's fluctuating between 607. Oh, by the way, when I move around, I change the background. So that's something I should try not to do. Sabrina, why don't we go with 608?
Okay, yeah.
I
Right,
saw
right
it
now.
go up to 610, but it's jumping around. This is going to
Going
be.
to stabilize a little bit when you're standing in that one spot.
I know, I know. This is why I stopped doing this lab, but I'm kind of mad. I wanted to see if I could overcome the lab. Do you know what I mean? It was a personal crusade, and you guys are coming along for it. So let's put our name at the top. This is lab number 6, the inverse square law. I'll adjust it in Blackboard in a bit after your class is done. And then don't forget to put astronomy 1020 and whatever your section is. Okay? Okay, so our source plus background at 10 centimeters is 608 lux. We don't have to write the units because it tells us that the whole data table will be in lux. All right, so now I'm going to turn the lamp off, and I want to do that without disturbing the setup. What's our background reading?
$24.
Good. You guys can subtract it and tell me the numbers later. Okay, I'm going to now try to move to the next position. 20 centimeters. You might think that we only have to take the background once, but every time you change the position, you change the position of the background. The background rays can be reflected, so we'll do the background each time. Let's do the background first before I have to reach down and plug it in. Let's just go with 18. We won't make this complicated because I've already wasted enough of your time with my bullshit today. Okay. Our artificial star is glowing. $200, 201.
I would say 201.
Yeah, I'd say 201 too, because that one stayed up the longest.
You guys keep subtracting those with your calculator and let me know what they are, because I'm trying to move quick here. All right, now we're going to move to 30 centimeters. Artificial star is a glowing. Let's see if I can get that lens flare again. Ooh. Okay. 96. And the background. $20. Notice the intensity is, or the source plus background is dropping, but the background is staying roughly constant. $40. Background, 21. Source.
What was the source and background for the for that?
Hold on, I'm fiddling here. I only have the background so far.
Oh, okay,
I'm
okay.
about to get the source
Didn't
plus
miss
background,
anything.
right?
Yeah, okay.
59. Do you guys have all this so far?
Yeah,
All right.
I have it.
All right.
Yeah.
50 centimeters.
The last column is where we put for subtraction, right?
Yeah, I was going to have you guys do that and read me the numbers, or I can do it with you. I don't care. I'm just trying to move quickly here because I took a long time in the setup. This is source plus background because the light. Do you see I'm alternating so I don't have to unplug quite as often? This is source plus background. 49. Ooh, weird. Yeah, okay. And then background. $26. Slide up to 60 centimeters. This is just the background. Wow. The background jumped probably because of the scattered light here. We'll just keep everything constant. $55. That's wild. See how when you move it around, the background can change quite a bit?
That looks like a negative, huh?
Say that again?
It looks like it's going to be a negative number.
No, the background was 55, but this is quite a bit lower.
Oh,
than
okay.
I was expecting.
Maybe
background's
67.
Okay, so the background plus source is 67. Okay.
I'm a little worried about that reading there. But science, we have to go forward here. This is the spirit of science. 70 centimeters. Source plus background. Fuck, it's, well, the background better be a lot higher. Sorry, I'm cussing. 86. This is why this experiment drives me crazy. It's
The
very
sun is changing. The brightness in the background is changing.
I hope it's the background. Let's hope our background's a lot higher this time.
Yeah, the background is changing. It's brighter.
Oh wow. Look at the background there. Because we're getting light from that lamp, which I probably should have
Yeah,
turned
it's
down.
coming bright. So 74. Oh wait.
74 good is good.
74.
Whew. 80. This is just background. Oh my God. It's getting brighter. The background.
Yeah, it is
Well,
getting-
let's just trust that it works. 91.
It's natural. It's nature. So 99, you said?
91. All right. Now we got the lamp on. 100. So we go with, and one more. 90. Ugh. A 100 again. And then our last background reading.
Wait, maybe I'm lost.
93.
193.
Okay. The experimental portion, the data collection portion has been completed. Okay.
Professor,
Yes.
is there any way real quick you could just pan the camera back to the sheet because I missed a few?
Yes, but hold on.
I can take a screenshot if you want. Like you can just hold it and then I'll take
yeah,
it.
but I need this desk so I can do the second part of the lab, which is just the graph with you guys. So can you just give me 1 sec here?
Yeah, no problem.
I'm wondering how good an idea this was. All right, just 1 sec. Okay, here's the data sheet. Can you see that?
I can see it.
Just give me a second here to get combobulated. Okay, we have a couple little last tasks to do, not much. Keep in mind, guys, that normally when you do labs that have a little more setup involved, you have a lab tech to help. And, you know, we do have a lab tech who helps a lot, but I'm not going to ask her to come to my home to set that stuff up. So I have to do a little extra here, you know? It's part of COVID life. Okay, do you guys have the subtractions? Can I trust someone to have done those subtractions correctly?
Yes.
All right. We're still recording, right? I just want to, do you guys see a recording thing on the screen? Okay, good.
Yeah, we still are.
Good. All right. What are our values start at 10 centimeters?
584, 183, 76, 38, 23, 12, 12, 9, and 7.
Okay.
I just want to say one thing. It could be because I calculated wrong, but I thought it's worth mentioning. I got -23, but that's probably wrong.
Well, at each stage, Kiana, the source plus background is always higher than the background. So there's no way you can get a negative. Does that
Honestly, I probably just calculated wrong or like put the numbers in backwards.
Just punch it one more time. It's quick to punch. Just punch it again. Can someone else verify that they got those as well? I was hoping everyone was kind of
Yeah, I
working.
got that.
I got the same thing.
Yeah, you're good.
Cool. All right, before we do the analysis, it's time for us to make a plot. Learning how to deal with graphical information is part of learning to get trained in science, because science is all about analyzing and understanding graphical information. And you'll find that even if you end up working for a car dealership or a business, these skills still come in handy. You have to do this in all types of careers out there. The first thing I want us to do is to change the scale on the x-axis. Instead of 30 centimeters, make it 10. I'm actually going to see if I can do this in pen. Do I have a nice dark pen somewhere? I have a felt, hold on, I have a felt tip pen somewhere. 1 second. Normally I advocate for pencil, but you guys kind of need to see what I'm doing. So I'm going to kind of use a felt tip pen. So things are a little bit clearer here. I'm going to turn this sideways. Come on. Shake. Okay. So cross out 30, make it 10. 40 becomes 20. 50 becomes 30. 60 is 40, 50. Are you guys following me here? 70, 80, and 90. Did you do that?
Yeah.
Okay.
No, can I see it really quick? So 30 becomes 10, and then 20, 30, 40.
10,
and so
20,
on.
30, 40, 50, 60, 70, 80, 90. Those are the values that we took over here.
1, 2,
Our goal is to plot source versus distance. Okay. Let's look at our top scores. This goes up to 180. Our first score is totally going to be off the charts, but all the rest should fit on rather nicely. So here's what we're going to do. 584 is, can you guys look at these scales here? Do you guys know how to figure out what each tick mark is worth? There's a strategy. This is one of the things I'm going to be teaching you in our labs. How do you know what each tick mark is worth? The way is you do the interval divided by the number of boxes. What are the intervals between these printed numbers?
4.
Oh, okay, that's the tick marks, yeah. But the point is the interval between the printed numbers was about 20. And there's 1, 2, 3, 4, 5 boxes. So if it's 20 lux over 5 boxes, sorry, you do the interval divided by the boxes, it's 4 lux per box, right? Okay, so prove to me that you can handle this. Count with me. How many lux is that?
4.
Here?
8.
Here?
Well,
12. Keep going.
16.
And then 20. Okay. Our first score, 584, is just way off the charts. So if anything, at 10 centimeters, we'll just put an X up there, meaning it's off the chart, okay? At 20 centimeters, we should be at 183, and this can easily go onto our chart. So start off at 20, stay on the 20 line. This is the intersection of 20 and 180, and that's 184. So I'm going to put my data point, I'm going to use a felt pen, right underneath the 184. And make your data point big and fat so we can find it later. You guys see how I did that? You with me? Good. How about at 20 centimeters?
So from the 10, it goes to 180.
Sorry, we were at 10. We got off the chart. 20.
Mhm.
Oh, fuck. Look. Oh my God. Excuse my language. Look what I did. Look at the dummy. Look at the dummy. I was supposed to do that at 20 centimeters. I deeply
Oh
apologize.
my. 20.
Sorry, guys. That's why we don't use pen. Okay, so what about 30 centimeters? It's because I'm holding this phone in my hand. It's like hard to do that and write. 30 centimeters, what's my source?
76.
30 minutes.
All right, so where should I go then? Here's 30 and 80. What's 4 below 80?
80 is 30, 80, 76. That's right.
That's 76 right there.
So, oh God, this is going to be so hard. Because
No, it's so easy because it's all right on the lines.
I
And
can't
second-
see. I'm blind.
Yeah, and I don't know if it's just me, but the quality is lagging behind a little bit.
Sorry.
That's
Can
all
you see?
right.
I have it frozen right now. Can you see what I've done?
There we go. That's a lot better.
Do not do that.
Hmm.
Do this and do that.
So, okay.
All right, how about at 40 centimeters?
38.
Okay, so where are we going to put that? Here's 40 lux and 40 centimeters. That's 36. So we should be right in between. Oh, whoa, 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 whoa. Every time I look through my screen and then I look down here, it's different. Okay. It helps to have a ruler here. You can see that that's 40 lux right there. So I just did it like half a box below. How about at 50? At 50, we have 23, right? So this line is 20. That's 24. Yeah, almost.
So in between.
A little bit in between. Okay, the next one is 12. Here we go. So this is 20. That's 16, and that's 12, correct? 70? 12 again, right? Now 9 at 80, that's 8. So 9 should be right about there. And 7 should be just above 6, 4, or just below 8. And this is our graph. Can you guys see that?
What is the last two?
The 80 was 9 lux and 90 centimeters was 7 lux. So this is 9 and that's 7. 9 is just above 8.
Okay.
7 is just below 8. Okay, let's see if we can make a best fit graph. I'm going to try to hold this in my chin. We want to connect the dots smoothly. It's not too bad, actually. Let me focus. You guys see that? Can you do that?
Mm-hmm. Somewhat.
So are we not connecting the X with it?
Are we what?
With the X at the top that was on 10, are we not connecting that at all?
No, because that actually is way, way higher. At 500, this is 200, 400, 500 would be like up here. So we don't connect that X. That X just reminds us that there is a point somewhere up there. Does that make sense?
Yeah, I was checking. Thank you.
Why don't we compare this to the graph of 1 over x squared in Google, and then I want to do a very quick analysis and then we're done. If you go to Google, come on, I don't want to lose my phone, or and you just type into Google plot 1 divided by x caret 2. Google's kind of dope like that it'll just plot this thing. And let's just zoom in on the x on the positive axis. You'll see that this is what the graph of 1 over x squared looks like, right? I think we kind of got the flavor of it, right? Okay, let's do an analysis and see if it came out any better. So you're going to be turning in 3 sheets for me today. The first sheet is your data collection. The second is your graph. And the third sheet is what we're about to do down here. Let's get the source intensity at 10, 20, and 30 centimeters. 584. I'm going to switch back to pencil now. $183 and 76. Okay. Let's say we use this as a reference intensity. If we were to double the distance from 10 centimeters to 20 centimeters, what would the inverse square law predict the intensity should be? So here, what we're going to do is we're going to predict what 1/4 of I sub 10 should be. So if I move and I double the distance, what should happen to the intensity according to the inverse square law? So the intensity is proportional to 1 over the distance squared. I've changed the distance by what factor? Does anyone understand what I'm saying? I feel like you guys don't understand me.
I'm a little lost.
You changed the distance by 10 centimeters, right?
That's if you subtract it, but by what factor means how many times did I change it?
2 times.
2 times. So what should the inverse square law predict? If I double the distance, what should happen to the intensity?
Go lower.
By what factor?
The amount of the distance, maybe?
No, it's not inversely proportional to the distance. It's inversely proportional to the square of the distance. That's what inverse square law means. If I double the distance, how will the intensity be affected? We did this with the law of gravitation. Did you not learn anything? Y'all scare me. Who else is out there? Mia, by what factor will the intensity drop? Shit. What does this symbol mean? I'm going to ask you a series of simpler and simpler questions until I start getting answers. What does that symbol mean?
Are you still asking me?
I'm asking anyone at this point.
It's proportional to?
Okay, so how do we use that? It tells me if you change the distance by this many times, the intensity will drop by that many times. How many times did we change the distance again, Mateus?
Twice.
So by what factor will the intensity change?
1/2.
No.
Square, like you said, right?
Look, if the intensity was inversely proportional to the distance, then if you doubled the distance, the intensity would drop by 1/2. The whole fucking point of this lab is that the intensity drops off as the inverse square as the distance, where that square is a big fucking deal. The whole point of this lab is that square. So if I change the distance by a factor of 2, the intensity should drop not by 1/2, but by
A square.
1/2 squared. What is 1/2 squared?
Is it the square root?
No, it's the square. The square is different than the square root. What is 1/2 squared?
1/4.
Thank you. This suggests that the intensity should drop by 1/4. So if I was at 584, what should it be when I get to I-20?
584 divided by 4.
146. What did we get?
183.
Is that good or bad?
Bad.
Kind of. What if we went to triple the distance, to I sub 30? If I change the distance by a factor of 3, by what factor should the intensity change?
Divided by 3, so it's going to be 584 divided by 3?
Nope.
No.
False. Once again, Mateus, this lab is about the square.
Is it divided by 9?
That's right, because 1/3 squared we should have the intensity drop by a factor of 9. If it was 584, we would expect to see 65. What did we get? 76. Whether or not this is good or bad depends upon our percent error. The percent error is your answer minus the true answer. Usually you take the absolute value to make it positive, divided by the true answer. Let's calculate our percent error for this one and for this one. Here, it's 183 minus 146. And let's say the true answer was 146. 183 minus 146. So 37 divided by 146, 25% error. Let's calculate the percent error here. 76 minus 65 over 65. What's the error there? You guys do that one.
I don't know if I did it correctly. I did 8. I got 8%.
Nope. You have to hit equals or use parentheses before you divide by 65. I mean, I just don't understand how you got 8. Look, if I do 76 minus 65, that's 11. 11 divided by 65 is 0.017. That's a 17% error. Well, I guess our data didn't come out that great. Did you confirm the inverse square law? Let's write 2 within 25% error, which is not great. It's not good for a professional scientist, but it might be okay for a crappy student lab. Okay. Well, I played some reindeer games. I'm actually doing that analysis section. Watching you guys flounder with proportionality symbols made me realize that this was a good exercise for you. I'm going to ask you some questions like this on the test, you know. If I change the distance by a factor of 2, how will the force of gravity change? How will the light fall off? Both gravity and light obey an inverse square law, which is why the name of this lab is called the inverse square law. All right. You will turn in your graph. You will turn in your data table. You will turn in your analysis sheet. Sound like a plan? Okay.
Professor.
Yes.
Real quick, I'm so sorry. I'm just slow at copying today. I don't know why. Can you go back to that sheet just so I can take a screenshot of it?
Yeah, he kept asking me, and then
Yes, that one.
she asked me, and I was like, no, I'm sorry.
All right, I got it. Oh, wait, can you go a little bit lower for that bottom piece? Unless that doesn't matter. Yeah.
Well, that was kind of scrap.
Oh, okay.
You might want to write down the formula for percent error. That was a new skill that I taught you today.
Mm-hmm.
So this is a skill for life. You know, employers that pay big money, they want their employees to be able to do stuff like that. That's the difference between clocking 80 to 90K a year and 30K a year. Okay. They want people who can do stuff like that. They pay you big bucks for this. And it's a cushy job sitting at a computer.
So we're gonna hand this in for telescopes and lenses.
All right, let's deal with that because I'm sure that's a little bit confusing. Because I changed my mind last minute, and I do appreciate you guys humoring me, we're not going to turn it in for lenses and telescopes. We are going to turn it in here. Share screen. Let's see if I can. Okay. Sorry, I just want to increase the speed of my internet here. Okay. Okay. Notice that down here, can I do this? I need to do a little housekeeping here, and I just want you to watch what I'm about to do. I am going to change this. So this is what you should send it to. You'll see a lab now right next to it called Lab 6 Inverse Square Law. And I think I did everything else. I didn't have a description, but I've got the 2 sheets, 10 points, unlimited attempts. So does that make sense? This lab, lenses and telescopes, I need to rename it. I don't know what lab this is going to be yet. I'm playing crazy with this class. Lab question mark. We'll get to that at some other time.
That's
Does
what I
that
was
make-
gonna say. So you can put like question mark for
Yeah.
not
I
knowing
don't
yet.
know. I might want to do it next time, or I might want to jump to sunspots. So I kind of just went off-road a little bit. I told myself I wouldn't do this, but I couldn't help myself. We spent 1 hour today. Do you understand? We spent 1 hour today talking about the inverse square law. I like it when labs connect to the thing that we did on the chalkboard. That's why I did that, if you can understand. I felt like that was good for us.
It makes
Also,
sense.
knowing that there's a lot of inverse square law questions in the test, maybe that's cool, you know? All right. Thank you, guys. I'm sorry for the setup time. How'd I do anyways? I lost track. 308. Yeah, okay. Not so bad. It's about an hour for a lab, you know, considering the setup time. So thanks a lot. Please turn those in. You know what to turn it in now to, right? Lab 6 inverse square law. Okay. Thank you. And I will see you on Thursday. Thursday's an important day, test prep. Take care of yourselves. Bye-bye.
Bye, Professor.